A mysterious object zipped through our solar system at incredible speeds in 2017. Dubbed ʻOumuamua, it is the first interstellar object we've ever detected. But by the time we realized it was actually in the neighborhood, it was already on its way out. With limited data, we aren't actually sure what it actually is, or where it came from. But simply being interstellar is not what sets ʻOumuamua apart. That honor goes to what we saw ʻOumuamua do. An event so strange, so in defiance of the laws of physics, that some scientists have turned to the explanation of alien technology as the only means to explain it. What is ʻOumuamua? What did it do? And are there more objects out there like it? I'm Alex McColgan and you're watching Astrum. Join me today in a deep dive supercut into our first interstellar visitor, the theories that surround it, and even plans to catch it up to settle the mystery once and for all. There are a lot of predictions in the science community as to how many extrasolar objects pass through our solar system. Some think we regularly see visitors, with up to 10,000 per day passing within the orbit of Neptune. That seems like a lot, so let's figure out why scientists think this figure is so high. The first thing to understand is that our solar system extends way beyond the orbit of Neptune. Beyond Neptune is the Kuiper Belt, and beyond that is the Oort cloud. The Oort cloud contains potentially trillions of comets that are gravitationally bound to our Sun. Some of the comets that we see that pass by the Sun likely came from and will return to this Oort cloud with their extremely elliptical orbits, taking tens to hundreds of thousands of years to do so. Some of the comets we see from the Oort cloud would never come to the inner solar system were it not for massive third bodies which perturb these comets' orbits with their gravity so that they fall towards the inner solar system. These third bodies are often other stars. You see, the solar system is not stationary like we sometimes may perceive, but we are constantly moving, orbiting the galaxy. As we move in our orbit, we cross paths with the gravitational influence of other orbiting stars. Even distances of a couple of light years can be enough to perturb a comet so it comes crashing down towards the Sun. On the other hand, it can also be enough for the comet to be pulled away from the solar system altogether, joining the ranks of the hundreds of trillions of interstellar interlopers found in the galaxy. As an Oort cloud-like body is likely not unique to our solar system, it must mean that comets are constantly being lost and others are being captured by stars throughout the galaxy every day. Although generally speaking, what we've seen of Oort cloud objects so far imply that the majority of comets in our Oort cloud did originate with our Sun, because they are mainly quite similar in composition. As the solar system travels through the galaxy, we also cross the path of interstellar interlopers that have been pulled away from their original home systems. They often approach from Vega, because that's the direction our solar system is heading through the galaxy. While the Sun does capture some of these objects, most are traveling so fast relative to us that they pass right through the solar system, only having their direction of travel changed as they pass by the gravity of the Sun. ʻOumuamua is one such object. ʻOumuamua was first seen in our solar system on the 19th of October 2017 and was spotted by the Haleakala Observatory in Hawaii. It was originally thought to be a comet when it was first discovered and got the classification C2017U1, but upon further investigation, it was reclassified as asteroid A27U1 when no coma around the comet could be seen, becoming the first object to ever get a reclassification like that. Once the orbit of ʻOumuamua had been established, it also became clear that it was traveling too fast for it to be in orbit around the Sun. We say that the object like this one has a hyperbolic trajectory. Because its velocity will see it leave the solar system altogether, it likely didn't come from the solar system to begin with. The object was thus given its Hawaiian name ʻOumuamua, meaning scout or first distant messenger. The International Astronomical Union had the unusual task of having to create a new classification of object just for Oumuamua. They decided upon I for Interstellar, so Oumuamua's designation is now 1I 2017 U1. As the first of its kind that we know about, scientists were excited to study Oumuamua, to learn what characteristics it might have that made it similar or dissimilar to objects found in our own solar system. Scientists quickly noticed that there was something strange about this object. It was small, perhaps between 100 and 1,000 meters long, and was believed to have an unusual shape, perhaps a cigar or a flat dish. It is believed to have this shape because its brightness pulsated over its 7-hour rotation period. This was because we received more light from its reflection when it appeared longer from our perspective. However, this could apply just as easily to a saucer-shaped object. It also appeared to be tumbling rather than rotating along a set axis. Oumuamua is unusual for more than just its shape. As it is like an asteroid, it must have originated from the inner part of its home system. So how did it get ejected and make its way to us? Is it from a collision of huge proportions? Alternatively, maybe it really is a comet, but as it traveled through interstellar space over millions or billions of years before it got to us, it had been coated in dust, meaning that the volatile materials typically found on comets weren't exposed to the sun. But while these elements were intriguing, the thing that really set Oumuamua apart from other objects was its motion. Oumuamua passed its closest point to the Sun on the 9th of September 2017 at a brain-melting 87 kilometers per second. But when it headed back into space, it didn't slow down like normal. Scientists watching it detected an inexplicable burst of acceleration, counteracting the pull of the Sun's gravity. Rob Warwick, who is credited with the discovery, said, "Its motion could not be explained using either a normal solar system asteroid or comet orbit." The rate of acceleration was minor, only about 17 meters per second when it was nearest the Sun, and yet this was enough to cause a stir in academia. Oumuamua was not doing what physics said it should do. In the next few months, scientists were able to observe it. Oumuamua was deviating from its path. In physics, objects can only accelerate when they are pushed. So scientists began to try and explain what was pushing Oumuamua. A few initial hypotheses were quickly ruled out. This did not seem to be simple solar winds giving a small nudge. While it is a recorded phenomenon for the small trace particles fired off from the Sun to push at objects in space, this small force was not enough to explain Oumuamua's acceleration, assuming it was an ordinary asteroid. Scientists reached for another example in our solar system of accelerating objects: comets. As comets travel close to the Sun, the ice within them warms and sublimates, turning into gas and spouting off from the comet's main body. This outpouring of gas and dust forms the comet's signature tail, but it also gives the comet a little push, acting like a little thruster on the side nearest the Sun that accelerates the comet away from the source of all that heat. But scientists could not detect all that dust and gas coming from Oumuamua. To be sure, the Spitzer infrared space telescope spent 30 hours trying to get any kind of reading on Oumuamua, but couldn't, meaning this object emitted nothing in the infrared. Typical comets have comas and tails that Spitzer can spot, like in this image. Adding further intrigue to the debate, readings from the Spitzer Space Telescope also indicated it was at least 10 times shinier than a typical comet, which would fit well if it were made out of something metallic. Then, what was Oumuamua? Let's take a look at an argument between two theorists with two theories. The first theory was the most headline-catching. Harvard professor Avi Loeb promoted in numerous papers that ʻOumuamua could represent alien technology. He argued in 2018 that solar winds could provide the acceleration seen with ʻOumuamua, but only if ʻOumuamua was actually much thinner than scientists originally assumed, between 0.3 and 0.9 millimeters thin. As a 1,000 meter long, 1 millimeter thin object was unlikely to appear in nature, Loeb argued that this had to mean it was artificial, a light sail created to catch solar winds and use them to accelerate through space from one star to another. This theory met the resistance from other members of the academic community. Darryl Seligman, our second theorist and a postdoctoral researcher at Cornell University, countered by co-authoring a paper in 2020 that said that perhaps the reason no outgassing was detected from ʻOumuamua was because ʻOumuamua was emitting an invisible gas such as hydrogen. This would not have been detectable using the telescopes that were trained on ʻOumuamua. Seligman proposed that ʻOumuamua was entirely or largely made of such hydrogen, a hydrogen iceberg that was sublimating thanks to the warmth of the sun, and it was that sublimation that was causing the push. Loeb disagreed. A few months later, he co-wrote a paper asking where exactly this hydrogen iceberg could have come from. He showed mathematically that the starlight in the interstellar vacuum was warm enough that any hydrogen iceberg that formed in even the nearest densest molecular clouds would have melted before they got here. Loeb was still convinced that an alien explanation was the most probable. His refutation was strong enough to send Seligman back to the drawing board, who dropped the hydrogen iceberg idea. However, Seligman continued to play around with the idea that ʻOumuamua had been moved by escaping pure hydrogen gas. Initially, he didn't have an explanation for how this could be, until in 2023 he met with University of California assistant professor Jennifer Bergner, who pointed to experiments in labs where water ice in extremely cold conditions, hit with radiation, could trap pockets of hydrogen, only to release it later when warmed up as the ice structure rearranged itself. As it happened, water ice is much more plentiful in space, and so is radiation. Cosmic radiation could be enough to provide the pre-baking that would be needed. Between the two of them, Seligman and Bergner wrote a paper arguing that ʻOumuamua needed a new category entirely. It wasn't a regular comet or an asteroid, but rather a dark comet, one with a coma that was invisible but present. Their explanation accounted for ʻOumuamua's acceleration and also for the lack of dust, as dark comets would not need to release dust as they were simply reconfiguring their structures and releasing the pockets of invisible gas, rather than blasting gas out from its surface like a small gassy volcano. While this was not enough to convince Loeb, who co-authored 2 more papers in the next month that accused Seligman of bad maths while also continuing to push his alien spaceship model, Seligman was already considering the next step in his own logic. He began to wonder, if ʻOumuamua represented a dark comet, could there be other dark comets out there? He, Bergner, and others began pouring through the data of objects already existing in our solar system. They might not be interstellar, but was anything else in the solar system accelerating when it shouldn't be? Sure enough, they found 6 that matched their criteria. 6 objects that showed non-gravitational, non-solar wind-based acceleration that couldn't be explained away by any known mechanism. These objects were small, some just as tiny as 3 meters across. They looked like asteroids and didn't have remarkable features. They were near-Earth objects, all orbiting close enough to Earth that missions to them were extremely viable. And they were all exhibiting signs of acceleration. To be clear, such acceleration was very minor, small enough to have been overlooked previously. These objects aren't zipping around the solar system from planet to planet like spaceships. They are not interstellar objects. But, just like ʻOumuamua, science cannot currently account for their motion, especially given that they do not have any visible signs of outgassing. And intriguingly, One of them is already scheduled to be visited by 2031. 1998 KY26 is due to be visited by the Japanese Hayabusa 2 probe, an asteroid sample return mission that was launched in 2014 and finished its primary mission 6 years later, but since has been given a mission extension to visit other asteroids in the near-Earth Apollo group. 1998 KY26 is rotating quickly, once every 10 minutes, and Hayabusa 2 will aim to perform a flyby to learn more about this water-rich, tiny object for the benefit of future humans. Exploring these dark comets within our solar system grants us greater insight into Oumuamua's nature. But what then of other interstellar objects? Have there been many others since Oumuamua? We've had other visitors from outside the solar system, but this next one is a little more conventional. Being the second I object, it's been given the designation 2I Borisov. Zooming in on Borisov reveals that this object had a big comet-like coma and tail, almost the size of 14 Earths across. We couldn't see it with the naked eye though, as the closest it got to the Sun was beyond the orbit of Mars in 2019. Borisov was roughly the same size as Oumuamua, about half a kilometer across. After its closest encounter with the Sun, it began falling apart. This is reasonably normal for a comet of this size passing by at this distance. Also, its composition, while uncommon, isn't particularly unusual either. Because it passed through the solar system at a greater distance than Oumuamua, its trajectory wasn't hugely affected by the Sun's gravity. So, overall, apart from its I classification, it's a somewhat unremarkable object. Now moving on to some other interesting interstellar objects that do not have the I classification. C1980E1 was originally a solar system object with an orbital period of 7.1 million years. The furthest its orbit used to take it was an incredible 1.7 light years away from the Sun. However, it passed a little too closely to Jupiter during its last approach in 1980. Jupiter's gravity accelerated it just enough for it to get a hyperbolic trajectory, and so this object will eventually become an interstellar interloper itself when it leaves our solar system in a few million years. On the other hand, we have had the opposite happen, where interstellar objects have had their velocities slowed down enough by the gravity of Jupiter that they became captured and locked into our solar system. Again, I mentioned Jupiter specifically because it has been determined that other planets aren't massive enough to do this, and it has to be a third body beyond the Sun and the comet that does the slowing down or speeding up. Machholz 1 and Hyakutake C1996b2 are potentially such captured interstellar comets from another planetary system. The giveaway for objects like these are their highly elliptical orbits and their very unusual compositions compared to the majority of other comets. This makes them interesting and viable targets for future missions, as the solar system might have done all the hard work for us in capturing interstellar objects and putting them within arm's reach. There's one more giveaway that an object might have extrasolar origins, and that is if it is orbiting retrograde to pretty much everything else in the solar system. An example of an object like this is 514107 Kuepa Oka Avela. What makes this object especially interesting is that it is also an asteroid, unlike most other interstellar objects we would expect to see. It could also be that the volatile materials have already burned off if it was once a comet, meaning it would have been captured very early in the solar system's past. Its orbit is also unusual in that it is locked in a 1-1 orbital resonance with Jupiter. While these objects are interesting, they don't settle the question of Oumuamua's nature, and there's much we still don't know. For example, where did it come from? We don't know, but we do know it came from very, very far away. To find Oumuamua's home star system, astronomers traced its path back over millions of years. It seems to have come from the direction of the star Vega in the Lyra constellation. Scientists found 4 possible home stars Oumuamua could have come from, some as far as 81 light-years away, but there haven't been any definitive answers on its origin story yet. And now it is over 6 billion kilometers away, moving at 26 kilometers per second towards Pegasus, about as far as Voyager 1 was when it snapped the famous pale blue dot image. Even if Oumuamua is not a piece of alien technology, it holds importance as the first confirmed interstellar object to enter our solar system. So it is no surprise that scientists want to take a closer look at it. We noticed it only 40 days after it passed its closest point to the Sun, but by then it was already 33 million kilometers from Earth. We sent ground and space telescopes into overdrive trying to answer the questions surrounding it before it escaped our grasp. But 2 months later, by mid-December, it was already too faint and fast-moving to be studied by even the largest ground-based telescopes. With limited data and more questions than answers, some researchers believe the only way to learn more about Oumuamua is to send a mission after it. However, catching up to Oumuamua is a significant challenge for 3 main reasons. The first obstacle is gaining enough speed to catch up. Oumuamua is over 6 billion kilometers away and careening through space at 26 kilometers per second. No chemical rocket that exists today can reach that speed, making a rendezvous difficult. And once we've caught up to Oumuamua, the second challenge is decelerating enough to actually study it. If we don't slow down, we'll shoot right past it and won't be able to collect any scientifically useful information. And thirdly, it is difficult to find such a small object in such a large galaxy. Remember, Oumuamua is just 1,000 meters long at most, tumbling through the vastness of interstellar space. Still, these barriers haven't stopped research groups from making plans to catch up. While accelerating to the speeds necessary to catch up with Oumuamua is difficult, it can be achieved through the use of gravity assist from other planets. The most famous examples of a solution come from Project Lyra, launched by the Initiative for Interstellar Studies. They've presented 2 different trajectories using maneuvers that have never been carried out in a real mission before, giving it a low technology readiness rating. Plus, if you've seen my video about falling into the sun, you know just how hard it is to do so. There is, however, another way to catch up to Oumuamua. The second trajectory proposed by Project Lyra is as follows. Launch from Earth, swing around Venus and Earth, conduct a deep space maneuver to reorient the probe, swing by Earth again, then use a gravity assist from Jupiter to catapult our craft towards Oumuamua. This plan doesn't require a heat shield, is a much shorter trajectory, and will result in a slower final speed of our probe as it heads into interstellar space. This would make it easier to decelerate on approach to Oumuamua and allow for better data capture. Project Lyra has identified at least 2 viable missions with launch dates between 2030 and 2033, and an arrival at Oumuamua at 2048. One of Project Lyra's mission designers, Marshall Eubanks, feels a mission to Oumuamua is inevitable. After all, researchers are crafting proposals for missions to planets of other solar systems, but even 100 years from now, Oumuamua will still be much closer than those destinations. But could there be a better way to get the data we want? What if we could have anticipated Oumuamua months in advance, rather than after it had already passed by? Astrobiologist Karen Meach of the University of Hawaii, who led the characterization of Oumuamua after its discovery, says we'll soon be able to do this for other interstellar interlopers that might cross our paths. NASA estimates that an interstellar interloper similar to Oumuamua passes through the inner solar system once per year. Since they're so small, they are hard to spot. Until now. The Vera C. Rubin telescope, set to become operational later this year in late 2025, would be able to spot these objects a whole 3 months before the telescope that detected Oumuamua. What's more, it will get busy building the Legacy Survey of Space and Time, a database of 2 million images taken over a decade. This data will be ideal for identifying changes in the night sky, including the trajectory of comets and asteroids. A 2023 paper estimated that the LSST could find up to 70 Oumuamua-like objects per year. Another initiative to better understand interstellar objects is ESA's Comet Interceptor mission, set to launch in 2029. It will park a probe in space for up to 3 years while waiting for a comet or an interstellar object to fly by. It'll then spring to life at the right time and carry out a close-range flyby to build a 3D map of the object. It will be the first ever mission launched with an unknown target. Sadly, we don't know how long we'd have to wait for another such object to cross our path. It would be a terrible waste of time, energy, and money if another Oumuamua-like object didn't fly past in that time frame. And these methods wouldn't give us any data on Oumuamua itself, which is now too far away for us to capture any new data about it from any of our telescopes. Whatever answers can be found there will be lost to the darkest reaches of interstellar space if we simply wait for another one. Evaluating these alternative options, maybe launching an interstellar probe chase on Oumuamua isn't such a crazy idea after all. It is technically viable. Nothing about it is impossible with our current knowledge and technology. But is it economically viable? Space missions require many resources: time, money, materials, brains, etc. Perhaps it is better to just let Oumuamua's answers go, trusting that, whether alien or interstellar object, if it happened once, it will happen again, and our solar system will eventually be greeted by its next interstellar visitor. Ultimately, it all comes down to, what is the price we are willing to pay to scratch the itch of our curiosity? Researchers at Project Lyra are certainly considering the investment. Is it worth it? In the end, multiple theories have been raised to explain Oumuamua and its strange properties. But without more data, we have no idea whether Oumuamua was another dark comet, or proof of alien life, or neither. It may turn out that none of the theories proposed so far are correct. That's the wonder of science. The more we explore the universe, the more we encounter strange and unexpected phenomena. And as we learn more about them, the better our theories become. Perhaps one day we will encounter more objects like ʻOumuamua from outside our solar system, which may lend further weight to a particular explanation. The search, even for dark objects that currently act under invisible forces, always fills me with a marvelous curiosity. Only time will tell if these missions to gain more data will be worth it, but that's the terrible, captivating irony of it all. Unless we take the gamble, we'll never know. Thanks for watching. Making this video required some long-term planning and work, which we were only able to do thanks to the consistency and sustainability of your memberships as astronauts on Patreon. A huge thank you to everyone who has signed up, and if you'd like us to make more videos like this, you can join with the link down below. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astrom content. I'll see you next time.